For centuries, geologists looked at the Earth and saw a static planet. The towering mountain ranges and vast oceans were widely accepted as permanent, heavy features, locked into the crust and fixed in place since their formation. In 1912, a researcher named Alfred Wegener proposed an idea that challenged that entire worldview. He called it continental drift, pointing out that the coastlines of South America and Africa fit together like a jigsaw, suggesting the landmasses had once been joined and later moved apart. The scientific community largely mocked his theory, and for a very practical reason. Wegener had no physical mechanism to explain how it worked. Solid continental rock cannot simply plow through thousands of miles of solid ocean floor on its own. Identifying a visual match between coastlines was an interesting observation, but it lacked a mechanical explanation. To accept that land masses actually move, science required concrete evidence of an active engine driving them. Fast forward to 1966. Geologists noticed that the modern margins of the North Atlantic Ocean perfectly matched much older faunal and fossil records. Identical species were separated by thousands of miles of deep water. This led a Canadian geologist named Tuzo Wilson to ask a strange and highly specific question. Did the Atlantic Ocean close up and then reopen in the exact same spot? This idea was incredibly problematic. It implied that an entire ocean basin, millions of square miles of rock, could completely vanish into the Earth and then perfectly regenerate itself along the exact same line. To prove an ocean could die and be reborn, researchers needed to find a planetary engine capable of continuously building and destroying the Earth's crust. The search for that engine starts underwater, at the mid-ocean ridges. These are massive underwater mountain ranges where magma constantly rises from the mantle and cools to form fresh oceanic crust. This animation illustrates a mid-ocean ridge generating crust. As the magma erupts and cools, it locks in the Earth's current magnetic polarity. In 1963, researchers Fred Vine and Drummond Matthews mapped these ridges and discovered alternating magnetic bands extending outwards symmetrically from the center. Because the Earth's magnetic field periodically flips, these bands act as a geological tape recorder. As new rock forms at the ridge, it pushes the older rock outward, leaving a quantitative, visible timeline of the seafloor actively spreading. But this spreading created a massive mathematical problem. If new crust is constantly being born at these ridges and spreading outward, either the Earth is inflating like a balloon, or crust is being actively destroyed somewhere else at the exact same rate. To figure out where that old crust was going, scientists looked away from the ridges and focused on the extreme edges of the tectonic plates, tracking where earthquakes happen. This graph plots global earthquake data by depth. An American scientist named Victor Benioff began mapping these tremors, sorting them meticulously into shallow, intermediate, and deep zones based on where the shaking originated. When you plot all this data together, it acts like a subterranean sonogram. The dots form a descending line, tracing the exact shape of massive, dense slabs of old oceanic crust diving deep down into the Earth's mantle. This plunging process is called subduction. Because the old oceanic rock is cold and heavy, it sinks. As it drops, it creates a massive slab pull effect, using its own sheer weight to drag the rest of the tectonic plate down behind it. This is the second half of the planetary engine. Subduction zones and slab pull relentlessly consume and recycle the old ocean floor, making room for the new crust erupting at the ridges. Tuzo Wilson combined these mechanisms of crustal birth and death into a cohesive model now known as the Wilson cycle. It describes a continuous 6-stage process where an ocean basin opens, expands, shrinks, and eventually closes. In the terminal stage of this cycle, the ocean shrinks entirely away. The continental landmasses on either side violently collide, thrusting rock thousands of feet into the sky to form massive mountain ranges. These collisions leave behind deep structural scars inside the lithosphere, called relic sutures. This is tectonic inheritance, the geological memory of where the crust has failed before. The scars left by ancient ocean closures dictate the future. When heat eventually builds up underneath a supercontinent and forces it to split apart, it naturally rips along these exact same relic sutures. The Earth breaks where it is already broken. This means the world map we navigate today is just a temporary snapshot. The Atlantic Ocean is growing right now, but eventually its inherited scars will tear into new subduction zones. The seafloor will be dragged back into the mantle. The ocean will disappear, and the